Hello everyone, and this is Vipul Purohit and you are watching my YouTube channel. So after a long time, my dear friends, I welcome you to the session of theoretical part. Okay, over the time I was posting the practical videos, so we now come back to the theory. In today's session, I'm going to explain you about a most important part of chemistry, and that is called as organometallic compounds. So here we go, organometallic compounds, which we also commonly call it as, in simple abbreviation is OMCs. Okay, organometallic compounds. So initially we will try to understand what exactly organometallic compounds are all about. Alright, and then we will go ahead and I'll explain you also what are the contents, okay, that we are going to discuss upon. So to begin with, when you talk about compounds, the very first thing, my dear friends, should come into your mind, and that is what? Oh yes, it's bond. Okay, a compound cannot exist without a bond. And bond, when you talk about, so it is force of attraction. Okay, and when I talk about force of attraction, my dear friends, there has to be at least two species. Okay, we cannot say that, okay, I love myself. Okay, people will say, oh, so such a selfish person he is. So always we have to have an interaction between two people. Okay, so that is what its force of attraction is all about. Same thing applicable is over here as well. So the two species which I am talking about in these organometallic compounds is, first one is organo and the second one is metallic. Okay, now when I talk about organo, it is resembling what? Organic. And when you talk about organic, you are very confident. Okay, I can also hear from your side, and that is the very first element which comes into your picture, and that is about carbon. Alright, so whenever we talk about organo, we talk about what? Carbon. But my dear friends, remember please, okay, in my previous video also I've already explained you this, organic versus inorganic chemistry. So carbon are of two types. Okay, we have an organic carbon, we have an inorganic carbon. So it's so very obvious when I use the word organo and when I use the word carbon, so it has to be what? Organic carbon. Alright, so we have an organic carbon. Alright, bonded with what? Yes, it's very simple now, and that is what? Metal. Okay, it is associated with what? Metal. Now my dear friends, the first thing which comes into your mind when we say metal is something, an element which is going to be highly electropositive, they have a tendency to donate electrons, blah blah blah. But here, my dear friends, we are making some changes in that. Okay, what we exactly mean by a metal over here, and that is we are referring to any element of the periodic table whose electronegativity is less than carbon. Okay, so let me once again repeat. Here when I talk about a metal, okay, so I'm not referring only to the calcium and the magnesiums and the sodiums and the potassiums and all that stuff. It also resembles those elements which have electronegativity less than carbon. I can give you some examples also, and that is, we can have boron, we can have phosphorus, we can have silicon, we can have arsenic. These are not conventional metals, my dear friends. Okay, if you can just concentrate on these are the elements of P block. Alright, and that also in the particular respective group they are situated towards the top. And you know very well that in P block, when I'm talking about group numbers from 13 to 18, and when I'm talking about elements which are situated towards the top, so that means they are generally non-metallic. But then still I consider over here in this context as under which category? Metal. The reason is because these elements have electronegativity less than carbon. Alright, so I guess this concept is clear. So we now go for the entire definition. Okay, I have explained you these in three parts. Okay, organo means we are referring to what? Organic carbon. Okay, next is metallic, so that means we are talking about metal. But then I go a step ahead by making very clear that what I mean by metal over here is any element having electronegativity less than carbon. And I'll give you examples over here. And when I talk about compounds, so there has to be a presence of bond, there has to be a force of attraction. Alright, so what we say is that organometallic compounds, which I very well say it as OMCs, so very easy to say that. Okay, a pet name, everybody likes a pet name, yes, don't you? So, OMCs is a pet name of organometallic compounds. So, OMCs are compounds where an organic carbon is attached or is bonded to a metal. Okay, and I put a hashtag. Okay, and here also hashtag. So I hope you understand that. Okay, what do I mean by metal? Okay, element with electronegativity less than carbon. Alright, so this is one part. Okay, attached, or I also call it as the word bonded. Now, the bonding which I am talking about, there are two categories, my dear friends. One category is, it's a direct bonding, okay, where a metal, the so-called metal, I can also say that way. So the so-called metal is directly bonded to the organic carbon, and I call it as organometallic compounds. Sometimes what happens is, the metal, the so-called metal, hashtag, okay, you understand these terms? So the so-called metal is attached to a carbon or is bonded to a carbon, organic carbon, by means of a pi electron system. Okay, it is also by means of a pi electron system. Now my dear friends, you must be knowing this, but then still I want to make you understand that whenever I talk about a pi bond, there has to be a double bond. Alright, single bond doesn't have a pi bond. Alright, so there has to be a double bond, or that's the reason we say pi bonds are additional bonds, because bond formation process takes place step by step. Okay, all the bonds, suppose if I have two bonds between the two species, so both the bonds are not formed simultaneously. The first bond is formed, that is going to be a sigma, and then later on the another bond is formed, and that is going to be what? Pi. So whenever I'm talking about a pi system, there has to be a what? Double bond. So here what am I saying is, the second option is that the metal is being attached to the organic carbon, the so-called metal, alright, hashtag. So the so-called metal is being bonded to the carbon, organic carbon, via what? A pi electron system. Now what does this mean is, okay, and that is very simple. I give an example, and that is, now I'm talking about an example of ferrocene. Okay, I got Fe. This is a pi electron system which I am talking about. Okay, this is a closed ring system which is containing 5 carbon atoms, and then because it is closed ring, so I call it as cyclo. Okay, it contains 2 alternate bonds, and therefore I call it as what? Diene. 2 alternate double bonds. Okay, that means it is what? Diene. So therefore we call this as what? Cyclopentadiene. Okay, so this is what the conjugated system, the pi system, which I am talking about. So what is happening is the Fe is being bonded over here. Similarly, over here as well. Okay, so there are 2 cyclopentadiene rings. Okay, and the Fe is going to be sandwiched in between the two. Therefore, we also call it as a sandwich structure. So here what happens is the alternate pi bonds which are there, okay, this is the conjugated system, is responsible to hold all the 5 carbon atoms together. And Fe is being attached to that alternate double bond of the conjugate system. So it means that Fe is being attached to all the 5 carbon atoms simultaneously. Okay, it is not attached to one particular carbon atom directly. Okay, so it is attached to what? A pi electron system. So this is the other option, my dear friends. Alright, so the first option is very clear, and that is organic carbon is being directly attached to a metal. Alright, so that means, say for example, I have a sodium and it is being attached to, say, organic carbon. Say for example, it is CH3. Okay, like this. Okay, with the charge of course Na plus and CH3 minus, so I get a carbon ion. So this is one possibility. Okay, where there is a direct bonding taking place, or otherwise the bonding can take place this way. Okay, so this becomes the definition of organometallic compounds. Okay, I take once again a recap of this, and that is organometallic compounds. Their pet name, yes, it's ONCs. So these are the compounds in which there are 2 possibilities now, and that is the metal, the so-called metal. That means all those elements with electronegativity less than carbon. So I given some specific examples also, that is boron, phosphorus, silicon, arsenic. Alright, they are being either directly attached to an organic carbon. Now you know, my dear friends, what is organic carbon is all about, where the proportion of carbon by mass is going to be what? High. Alright, so such so-called metals are directly being bonded to the organic carbon, or the second possibility, my dear friends, is, and that is that these so-called metals can be attached, can be bonded to the carbon, organic carbon, via a pi electron system. So this is what the example is. Alright, so this is what is the definition, or what we call it as introduction of organometallic compounds, and I'm sure you have understood up to this very well. Yes, my dear friends, once you understand what exactly organometallic compounds are all about, we move on to the next part, and that is the types. So types of organometallic compounds. So their broadly classification of this is, okay, and that is 3 types. The first one that we talk about, called as ionic organometallic compounds. The next category is sigma bonded covalent organometallic compounds. And the last one, the third category, is multi-centered electron deficient organometallic compounds. Okay, so we are here into the classification or the types of organometallic compounds. So broadly they have been classified into 3 categories. The first one is ionic organometallic compounds. The next one is sigma bonded covalent compounds. And then the last one is multi-centered electron deficient compounds. Very brief explanation of these is, and then we can proceed to the next part of this particular chapter, and that is to start with the ionic organometallic compounds. So the word itself, ions, so you understand that yes, there are going to be charged species. And because we are talking about compounds, and as I referred, that compounds involves bonds, and bond is force of attraction, and force of attraction always exists between oppositely charged species. Okay, so I guess the term gets very clear to you that we are talking about those organometallic compounds which involves ions, and it involves bond formation between the 2 oppositely charged ions. Alright, next thing is, when we talk about the stability, okay, of these ionic organometallic compounds, it is basically related to the carbon ion. Okay, the stability of this is related to what? The carbon ion. Now how it is so? And that is, stability of carbon ion is to be considered over here. How it is? I give you some examples. Example number 1, and that is, if I am having a highly unstable carbon ion, say for example it is S plus and C2H5 minus, this one. Okay, so this is unstable carbon ion, so we say the reactivity of that is going to be high. Okay, reactivity of the organometallic compound is high. Okay, next, if I'm talking about a moderate stability of the carbon ion, then example is Ca2 plus C6H5 2 minus. Then we say the reactivity is less. Alright? At the same time, if I have a carbon ion, okay, with an extended conjugated system, then that is going to be more stable compared to the simple unconjugated system. Once again I repeat that if I have an organometallic compound, okay, with extended conjugated system, or we call it as what? Delocalization of pi electrons. So they are much stable as compared to the simple unconjugated system. I give an example for this, and that is CH2 double bond CH, CH2 minus. Okay, so there is a conjugation over here, and this is supposed to be what? More stable as compared to the unconjugated system. Alright, so this is in brief about ionic organometallic compounds, where we talk about the stability of the carbon ion, okay, is related to its reactivity. If the carbon ion is highly unstable, the reactivity is high. Okay, and if the carbon ion is stable, the reactivity is less. Alright, I hope it's very simple and it's going into your brains very well. Right, we go into the next part, and that is we talk about sigma bonded covalent organometallic compounds. This involves simple normal bonds. When I talk about normal bonds means, as I said, bond is force of attraction and there has to be two species. Alright, so there is a bond formed between the two species. So that means there are two centers. And I'm talking about a single bond, my dear friends, because I'm talking about sigma. Okay, as I already mentioned before also, not in this particular video, and that is, when I talk about pi, so that means there are additional bonds. When I talk about sigma, so I'm talking only about a single bond. And when I'm going to consider a single bond, so that means there has to be only what? Two electrons. So, the normal bond which I'm talking about, is referred to as two electron, two center bond. Because the force of attraction exists between the two species, so I got two center, and because there is going to be only one bond contains two electrons, and therefore we say it's going to be two electron, two center bond. Alright, I give you some example also, and that is Zn, C2H5 twice, or we can also go for Hg, C2H5 twice. Okay, so this comes under the category of sigma bonded covalent organometallic compounds. Okay, so in these compounds there are no pi bonds. Okay, so we just put this into this category. Alright, so this is a brief explanation about the sigma bonded covalent compounds. Okay, now a brief explanation about multi-center electron deficient compounds. Alright, now electron deficient you know very well. Okay, and what is electron deficiency? Deficiency means what? Less. Okay, less than the minimum number of electrons required. Okay, then those compounds are called as what? Electron deficient compounds. Okay, so I give you some examples of that, and that is, we are going to talk about BeCH3 twice. Okay, at the same time I'm going to talk about, say, AlCH3 thrice. Now, my dear friends, these are all polymeric. Okay, these are what? Polymeric. Okay, how the polymeric form looks like is, okay, there is some bridge bonds also. The methyl groups are considered to be the bridging ones because they are going to connect. Bridge means what? Connection. The two metal atoms. So, for BeCH3 twice, I can just show the structure over here, a hashtag, and have a look over here. It is BeCH3, CH3, Be, like this. Okay, so this is polymeric in nature. Similarly, I show the structure of AlCH3 thrice. I just put a star mark over here and you can have a look at it. AlCH3, CH3, the dimeric form. So you can have a look at it. There has to be 6 methyl groups because for a monomeric form it's going to be 3. So for a dimeric form we have got how much? 6. So I consider this as a dimeric form. Okay, and you can check it out that the methyl groups over here are going to behave as what? Bridge. Okay, and those bridging bonds are going to be what? Not so stable enough. And at the same time, how they are going to be represented as, can you see this? AlCH3Al. Okay, how they are represented is there are 3 centers, but then there are only 2 electrons. Okay, so I call these as 3 center, 2 electron bonds. Okay, here when I was referring to normal bonds, it is 2 center, 2 electron bonds. But here when I'm talking about bridging bonds, the bonds are not so very strong enough as compared to the terminal ones. See, if you can see this, AlCH3, AlCH3, these are terminal ones. This also are terminal ones. So 4 of them are terminal ones. Okay, and these 2 are bridging ones. So if you are going to make just a comparison between the bridging and the terminal ones comes out to be much more stronger. Alright, and the bridging ones are going to be the 3 center, 2 electron bonds. Alright, so this is very short. I have given you an insight, not a detailed explanation, just an insight about the broad spectrum of the classification of the types of organometallic compounds, okay, we are going to consider three basic categories. The first one is ionic organometallic compounds, then sigma bonded covalent, and the third one is going to be multi-center, because you can see this, okay, center is generally referred to a metal, and when I'm talking about a polymeric, I'm talking about dimeric, so that means obviously the metal is going to be more than one, and that's the reason we call it as what? Multi. Electron deficient, yes, of course it is electron deficient, because if you can check it out, BeCH3 twice. Okay, so beryllium is going to be at the center. It is going to form two bonds, and two bonds means 4 electrons. Okay, so when I'm talking about deficiency, I'm talking about with respect to octet. So it is less than 8. Alright, so that means it is electron deficient. Similarly, trimethyl aluminium, which I have shown over here. Okay, so that means 3 bonds is being formed by aluminium, central aluminium. So total are 6 electrons. Once again, it is less than 8, and hence it comes into the category of electron deficient compounds. Alright, so these are the examples. They are existing in the polymeric form, in the dimeric form, where we have the bridging methyl groups. Okay, they are connecting the two metals. Alright, so I hope you have understood the types of organometallic compounds very well.